in the last segment we talked about the conditions or assumptions which are required both from the perspective of the geometry of the beam which is subjected to some load, plus the conditions on the loading, so that the case of pure bending will exist. And in this segment what we will see is what sort of deformation will happen if those conditions are met. So, just see this. Now, suppose we have a prismatic bar like this, and for simplicity and to consider that the section need not be, consider the condition that the section need not be a rectangle, you can think always that it is an isosceles trapezium. Okay. Yeah, so I can draw in fact always that to keep that thing okay, and here I can draw the cross section maybe like that. It has to be symmetric about the center line. So suppose this is the center line. Yeah. And we are having moments applied like this. And if you remember, in the first segment of this unit, I talked about how and why the moment, the value of the moment is constant throughout this length. Okay, it cannot change. Any section you pick, the same moment exists. Okay. Now, if you cut this side, you will see that the same moment is getting applied here. If you cut this segment, if you keep this segment as free body diagram, you will see that this kind of moment will be acting. Okay. So, that means everywhere the moment is same. Now, if the moment is same throughout, now there is no reason why the bending, the amount of bending that will happen will differ, because everywhere the condition is same, so everywhere the bending must be same. And if that is so, then obviously we will safely assume that the deformed shape will be, I'll take these things a bit up, whatever space is available, so that we can, yeah. So, we can safely now assume that once it is bent, we will have something like this. Okay. And everywhere this cross section is same, okay, though in the drawing it looks thicker here. Anyways, so now the radius of curvature at all these points must be the same, and we can in fact assume that somewhere it goes and meet. Okay. So, this there is a constant radius of curvature throughout, because there is no point along this axis is spatial. So, everywhere the radius of curvature has to be same. These are all happening because we are considering always a small deflection, not very big deflections. Okay. Remember the word which I from the beginning I have been using, a little bit flexible, okay, not too flexible. And if that happens, what other thing can happen? Yeah, suppose you had drawn some lines over here, okay, for example like this you had drawn, and like that. These are just lines which you had drawn on that beam, assume now for the sake of simplicity that it's a rectangular beam, okay, which will be true for the trapezium also, but it's easier to imagine for a rectangular one. Now once you bend this, what will happen is all these things will take the shape of circles. How many I had drawn? 3. Like that. And these lines, the vertical lines, will all be pointing towards the center. So if I draw like that, so this will be like this. If I draw like that, this will be like this. And yeah. So whatever. I haven't counted how many I had drawn there. Yeah, assume that these number of lines and these number of lines are same. Okay, so this is how the new shape will look like. Now observe one thing, that see, if you consider any of this square or rectangular segment, and suppose that has changed to this, okay. Now think about this angles. All these angles were 90 degrees here, and what happened to them here? Now also they are 90 degree because these are circles and these are radius. So they will always meet at 90 degree to each other. So that means your shear strain in this plane, in fact if I draw, say suppose this I consider to be x-axis, this to be, it's bad, right? Suppose this is say y and the z-axis is coming out of the blackboard, then all these gamma xy's are 0 because 90 degrees are remaining 90 degrees after the deformation. So there is no strain, shear strain for that matter, in xy plane. And then exactly the same thing if you draw such things on the top surface, that is on this surface. If you draw these rectangles, you will see that all of them remain, in fact that's even easier to see that all those rectangles remain rectangles, so none of them changed those 90 degrees to anything else. That means the shear strain in that YZ also remains 0. So that means all the shear strains are 0. Okay, and in fact we are not applying any normal forces in this direction, so the normal stresses also will be 0 in this z direction and in the y direction. Okay, so that means we will have, because of this kind of a deformation condition, what we are having is a situation like this, that the sigma y is sigma z, they are 0, plus all these tau xy, I'll put equality sign maybe, tau yz equal to tau zx, everything are 0. Now only thing which will remain is the normal stress in the x direction, which is the sigma x. Okay, why this will be non-zero? Because you see this, we will discuss all these things quantitatively with equations. Here we are discussing it qualitatively so that the picture will be clear. Think about the fibers which are towards the top surface. Okay, for example, the fiber named say A. So this is the fiber named A, and this is the fiber named B, which is towards the lower surface. Okay, now Before we applied the moment, the length of each fiber were the same, the length of the beam. But now you see the length here of the fiber, it has reduced because the radius here is smaller than the radius here, but the angle is same. So that means the length of the circumference, that sector, okay, at A will be smaller than that of B. So that means in some of the fibers at the top, means near the tops, as we go from here, I don't know where that transition will happen from compression to extension, if we can think like that. So A has got reduced in length, that means those fibers are in compressive stress, and these fibers like B, which are which have been elongated, they obviously are in a tensile stress, state of stress. Now where this transition happens from tensile to compressive, because somewhere it has to happen, and because there is no if something goes from a positive to a negative, okay, the tensile is always considered positive and compressive negative. So this from positive to negative, somewhere if it goes, so somewhere in between it must be passing through the value of 0, and we don't know yet. In fact, that also will be a object of our calculation. Now but somewhere along this line the transition will happen. So some of the portion maybe who knows. So some of the regions maybe here, they are under compression, and these are under maybe tension, okay. So some, and then where this line exists we don't know, and I don't want to make any guesswork now, because we will discuss. You can have a guess where it will happen, okay. Yeah, it will be, so that drawing is slightly wrong because it will be slightly towards the lower side. We will see why in a moment or in the next segment. Yeah, but the point was, this will not be 0, this will be positive for some of the fibers and it will be negative for some of the fibers. So that means again this state of pure bending is very similar to the case of axial loading, where you had on the planes which are normal to the axis of the beam, only the axial loading, the normal stress was there, no other stress. And here also, if you consider the planes which are normal to the axis of the beam, on that there is only one sort of stress is acting, and that is the normal stress. That means in both those cases only normal stress is the stress which exists, but the difference is in axial loading over the full cross section it was the same kind of stress. If it was tensile, the whole cross section it was tensile. If it was compressive, the whole cross section it was compressive, and of the same value throughout. But here, as opposed to that, first thing, some portion it will be positive, compressive, some portion it is tensile. Along with that, even this stress will not be the same value throughout, it will change. But whatever it will be symmetric about this plane, because there is no reason why it will be not symmetric about that, okay, because everything, the geometry, the loading, everything is symmetric about that plane. So the stress that will be developed also will be symmetric, okay. And yeah, one more thing is that, see, all these planes which were planar before you applied the load remain planes only after you apply the load. Okay, that means planar sections remain planar after you apply the load, just they become means rotated with respect to their original position. Other than that, nothing happens. And yeah, so there is no warping that happens in such conditions when there is pure loading. Means symmetrical loading of this moment. There is pure bending. Okay, so this is about the deformation pattern and what. One more point which I can make is, if the condition is not of pure bending, if the bending is slightly impure, then these kind of nice things doesn't remain anymore. You will have, you know, different segments would try to slide along or with respect to each other, and the situation becomes much more complex. Okay. There are two different names which are being used. These conditions, when they prevail under with a beam, they are called the Euler beam. Okay, the Euler beams. And when the shear stresses also are significant, so that you cannot neglect them anymore, and then those beams will be called Timoshenko beam. Okay, so for our study we will be concentrating. We will see if time permits, we will talk about Timoshenko beams. Otherwise, we will stick to mostly the Euler beams, where all these conditions are satisfied and things are simpler. Okay, so we will stop here for this segment, and we will meet in the next segment, where we will use this deformation pattern, the concept of this deformation, plus the concept of this state of stress, and we will quantify them. We will write their corresponding equations, and from there we will find out the distribution of them. We will find out relationship between the applied moment and the distribution of the stress, the way we did for the torsion case, right? We applied a moment, a torque, and we tried to correlate how much or what is the distribution of the shear stress depending on the applied torque. Similarly, the twist which happened with respect to this applied torque. Similar things which we will do for this condition, that the distribution of sigma with respect to or as a function of m, which we will figure out. And then yeah, so that's the major thing which we will do, and later on we will see can we figure out the deflection. As I said, the twist we were calculating, in this case it will be the deflection of the beam. So that is also a point of discussion which we will see, and then that will not be under the pure bending case. We will see that is more interesting once we go for an impure bending case, where even the shear stresses will exist along with the bending moments. So these are the things which we will discuss, and mostly the quantification of all these things which we discussed qualitatively now will be the topics of the next segment. See you in the next segment.